just to tell you in advance, we will be using Nuke's copycat as the example, because that's at the moment the best tool to do machine learning in for any compositor, and it's actually kind of really cool. So, but this won't necessarily be a tutorial on copycat. I will direct you towards those resources as well. This is more kind of to give an actual understanding of what machine learning is, and yeah, so it's more about the kind of background, the kind of thinking behind it, and then hopefully by understanding that a little bit better, you will be able to play around with copycat in Nuke as well and see what it is that it's actually doing, and kind of how to interpret what it does. So yeah, let's get cracking with that. So first of all, there is at least two different types of machine learning people use. There is supervised learning and unsupervised learning. And supervised learning works by giving an example. So you give an example, and the machine will try to do that. Unsupervised learning works without supervision. So what does that mean? How can you have unsupervised learning? So, and a lot of these principles that we discuss here for machine learning, that's actually applicable to education overall. So here's an example of unsupervised learning. So here's a human child, and they've been given a toy which kind of has a lot of body parts and to put together, but they were just doing it on their own in the other room before I got to that to see what they're doing. And interestingly, rather than actually putting them together, what he has started doing instead is he started putting all the legs together over there, all the shoes, or all the legs and toes together over there. And here we have all the hands, and this is actually a stack of different heads. So what this actually is a good example of is a prime example actually of unsupervised learning called clustering. So clustering is a technique which we don't do too much in Nuke. I'll show you one example where it might actually be happening behind the scenes, but we leave the exact algorithms up for kind of educated guess. But how clustering works is, if you just look at this. So first of all, I wanted to just quickly show you this as well. This is what machine learning often looks like when you try to do machine learning in a university, and it's quite dense, and really, this is actually the question, and then this is the answer. It's like, okay, that's and this is just the basic statistics before you get into the deep machine learning stuff. That's all cool, and for the people who develop machine learning algorithms, this is very important, and that's the concise ways for them to represent stuff. But what I will try to do today is make you understand some of the principles in hopefully a little bit more visual way, because in the end, this is actually what's happening in a lot of the times here as well. This is from some exam papers I took in some exams some years ago. Anyways, so going to this clustering idea. So first of all, unsupervised learning. So we have this algorithm, and one example of that is the k-means algorithm. So k is just a letter that you could use to say how many clusters you have. Let's say 2. And what you do is you have like some kind of 2-dimensional data, and you say, just you have a good guess, maybe there's 2 clusters in that. How you guess that, that's another topic. But you guess that maybe there's 2 clusters, and what you do is you just randomly put those centers of those clusters somewhere, and you pull a dividing line between those 2 centers. So there's a blue center and the red center. So you pull a dividing line like that over here, and then now you just categorize all of those data points on that side belong to this cluster, and all of those data points on that side belong to that cluster. So then you look at the values of all of those data points. So if I look at these values in here, they go from -2 to +2 in this axis, and -2 to +2 in that axis. So for example, that value in there is from -2 to -2. This one is kind of close to 0, 0. That's +2 to +2. So what you do is you take all of these values and average them together. And whatever the average value is, you will put that as the new position of the center of this cluster. So that will be the new center point. Then you draw a new dividing line through that. So it's like a, just a perpendicular line between the two. And you reassign everything now to be in that cluster or that cluster. And then you calculate those values again. What will be the average value of this cluster? And then that will move this to closer. You do it again, you do a dividing value in here. And eventually what will happen is that where you have the most points, like, that's the center of the cluster, that will then be the center of this cluster, and you have this hard dividing line. Now we've divided these points. And this is, by the way, this book is by this guy called Zeliski, and this is free. It's a very expensive book, but this guy is very generous, and he puts up drafts of his next edition of this book online so that people could copy read them and just make sure that there's no errors in them. So get this book, good book, Computer Vision Algorithms and Applications, really good book. Anyways, so that's one algorithm. It doesn't need any supervision. You basically give it some data, and what it comes out with is clusters. So what kind of data could this be? You could say sort all the fruits. So for some way, you've given your computer lots of fruits, and it will sort them. It might sort, for example, all of the. Is there a link to this book? Yes, I think you can get this book. Let me just move my little thing is around in here. Zeliski book. This is my downloads. It's his own Dropbox. See if this works for you. I'll drop it in the chat in here. There you go. See if that works. Anyways, so going back to this book. So cool. So, but it's unsupervised. The data will sort itself out, and but we don't know how. So if you give it a bunch of oranges and apples, it might actually sort things as like, here are small fruits and these are big fruits, or these are yellow ones, these are green ones. So it doesn't really, you don't really know what it has sorted, but it has sorted it. So where could this be useful in compositing? So for example, we have different clusters of colors in our images as well. So for example, if I just take all the red, green, blue values, it gets really dark in here, never mind. Then, and I take those red, green, blue values to represent X, Y, Z coordinates in space, you can begin to see that maybe we could actually cluster some of this. So in this footage, probably a lot of this stuff is green screen. Huh. I am now in the dark. I think this space needs motion sensors, which don't really work here. Never mind. I'm in a classroom, which is dark. Cool. That aside. So, anyways, so we have this potential clusters in here. You could say anything that is green is, maybe that's all background there. So, right. So, for example, Primat might work in that kind of way. So if I reset this, let's reset this, and you press auto compute, what it actually is doing behind the scenes is it's putting all your values into this kind of three-dimensional space, and then it makes a polyhedron around those values automatically. So it is using some type of clustering already. It's saying those are background, the rest is foreground, and the ones in between, maybe these are edges or these spill areas. So it is, we do actually use these unsupervised methods. Of course, later you can add your own supervision to that, say this color should also be background, and then you start modifying these polyhedra within that. So yeah, clustering is one unsupervised method. And the other kind of way that you could, for example, cluster things inside Nuke if there were points. So for example, you could do this, which is if X and Y are represented as colors as well. You could cluster things according to X and Y. And let's say this here is the brightness of the image, the third dimension. Then if I view them in space, I could now see that actually maybe I can find a cluster of points together, like, maybe everything around this area here is one cluster. And in fact, I could actually find clusters, for the tracking markers in here. So these are the tracking markers, and maybe he can perform a different cluster or a few clusters. I don't necessarily know how many clusters I have in my image, but you could have clustering based methods to do image segmentation, for example. And even better is if you have a clean plate of the background, then you can have a cluster of values that, they belong to the background. So anything that's not in that cluster, maybe it's the foreground value. So clustering. Did I say clustering enough? Clustering. Unsupervised. So that's how unsupervised learning works. There are additional learning methods such as reinforcement learning, which we'll not be covering today, but there's unsupervised and supervised. Cool. We will come back to this supervised in a bit. So, but before we do, let's learn something else. Let's learn the idea of optimization. So, for example, in here, we have a picture. And what we have in this picture is we're just trying to take one of these points in there, that one, and we try to find this in the next frame. So I think it's frame 89 and 90. So we're trying to find what is the transformation that takes it from one point to the other. And we would like to kind of make an algorithm that does it for us. So what we could do is if we crop just the area that we're actually interested in. So here's our tracking marker, red, green, blue. Here's our tracking marker on this frame and the next frame. I've just added a little bit of noise to it. I don't even remember why, just for fun. So that's that frame. On, that's how much this point has moved from one frame to another. So what we might want to do is we might want to figure out, well, what is the transformation? And just the kind of position we'll do. So if I pop out this transform from here, let's do this. So if I want to make these things match, I want to know, how do I measure that they are matching? So how do I know that I have reached, achieved a match? So I need some kind of a measurement. And in machine learning, it's often called a error function or a loss function. We can call it either a loss or an error, but we need to measure it somehow. So one way of doing this is if I look at the difference between these two images. So they don't overlap ideally. So if they don't overlap ideally, if I subtract one from the other, there will be some difference between these two images. And what I could do is I could measure what that difference is. And one easy way of doing this inside of Nuke, for example, is if let's split this viewer in here, let's split that way. And I'm just going to use the pixel analyzer in Nuke. So Windows pixel analyzer, this nice tool that we often forget exists inside of Nuke. And I'm just going to take an average of all these pixels. So there. So I just want the average value of all these pixels. So for the whole image. So I have one number, and this one number will be my measurement value. So it's like, now I know whether I've got it or not, the smaller this value is. So I want to make this error. If they don't match, then this value will be bigger. But if they overlap really nicely, then this overall average will be smaller. And I'm just going to, because in here, it's mostly a green image, I'll just look at the green value in here. So if I start optimizing this, I have two parameters, X and Y. So it's a two-dimensional space I'm trying to navigate. And I'm just going to start moving in one direction. So I will look at this value in here, and I want to see if this one starts getting smaller or not. So I will look at it now. It's like 1290 or something. So I look at it now, 123. So okay, smaller. 123. 1227, even smaller. 1, 2, 4. Okay, now it's not smaller anymore. So I have gone too far. But let's do the other value as well. Let's do y. So let's start making it bigger. So let's see. This is 1, 2, 4. So now it is 1, 1, 3. Okay, it became smaller. 1, 1, 2, 6 smaller. 1, 1, 9 smaller. 1, 2, 5 bigger again. I went too far. So this is when you could be like, okay, now that I went too far in that direction, maybe I switch direction and go back in the same direction, but not in the same increments. So the increment that you choose, so at the moment I'm moving 1 pixel at a time, that is often known as the learning rate. So how fast do I navigate the space of possible solutions? So I'm going to do it now in smaller increments. At first I was making the X values bigger. Now I can make them smaller again. So let's go down. So we'll start going down. And what we want to see is at what point will this number stop becoming smaller? So it's 1 to 4, 1 to 3, 1 to 2, 1 to 2, 1 to, and I think at that stage there it starts getting bigger. Okay. The same with this. Start making it smaller. So we can see this number is becoming smaller here. That's the average value. 1, 3, and at that stage it starts getting bigger. So try again. Let's go back in the other direction until this value stops getting smaller. And let's try this one. Let's go in the other direction. So 142, 141, 140, 139, 138, 137. And I think somewhere there it starts getting bigger. So overall, eventually, you will, hopefully find some kind of a minimum. So if you now look at this, where it was before and where it is now, compared to where it used to be. So we've made it move that much. And I think we are, at least we're closer than where we used to be. And the principle is that by moving these two parameters, we estimated, this X and Y by looking at this final result. And the final result is the difference between what I want to get. I want this to be where it needs to be and where I am at the moment. And I'm taking that average difference. And I just want to minimize that. So one way you could visualize this is if this is like a 2-dimensional space, and let's get rid of these red ones in here. Scroll, 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 scroll. And let's get rid of this. So, and let's expand this. Just need to move you guys down here somewhere as well. There. And let's float this window. So I was changing my X and Y values. So at first I was making my X values bigger, and we sort of started somewhere on this surface randomly, somewhere there, and I was making my X values bigger. So I was moving sort of in that direction. At some point, my error, it was getting smaller, but at some point it started getting bigger again. At that stage, I started moving my Y values and was making my Y values bigger. So moving kind of down in the spacing until at some point, again, it stops becoming smaller. So then I move my X values again, or I change direction, move my X values maybe in that direction for a while, and Y values in that direction. So these choices, whether to change direction, but basically what you're doing is you're kind of trying to find the bottom of this bit, which is where is the smallest error. Because if I make my X values too big in one direction, my tracking markers will not overlap. If I make it too big in another direction, they won't overlap. It's only this kind of the minimum right in the middle where they overlap, and that's the minimum we're trying to find. And as a process, what you're actually doing is you're looking at the difference between this change and the previous change, and by doing that, you're doing a gradient. You're looking at what's the difference between this frame and the previous frame, and you're kind of moving in direction of some gradient in there, and they call it gradient descent for that kind of reason. There's a bit of a simplification in here, but that's initially the idea of gradient descent. You optimize, you minimize the error, whatever you're trying to do, by adjusting the parameters and trying to find the bottom of the pit where you have the smallest error. So we have just learned optimization and gradient descent. Cool, without having to look at all the integral signs or derivative signs, which would have been actually the ones for gradients, regardless. So, but that's the idea. So hopefully that makes sense. If you have any questions, drop it in the Q&A. I'll happily answer some of them. So now, half a century ago, some clever people, I'd like to call them McCulloch and Pitts, but I might be misremembering their names. They come up with a sort of an algorithm that is like a very simple version of a neuron, like the one that you have in your brain. So the idea of that, I'm just going to reset my workspace now because I don't need this pixel analyzer for now. So reset workspace. So the idea is that you have values that come in and you have weights on these connections, and you combine those weights. So very simply, it could be, if this is coming in from here, this weight is -1, so -1 times 0.3, and this weight is coming in from here, so this is +1 for this weight, and that's the value. Multiply that and add it together. This is your output value. So Federico says, yes, what we did earlier is we minimized the gap between frame 89 and 90. Exactly. That's what we were doing. We were changing the X and Y values, and we were choosing the type of X and Y values by moving those X and Y values, which will give me the smallest difference between those two images. So my X and Y values in my transform node, X and Y, I was making them bigger. So I was kind of initially moving in that direction. And the loss in here is the loss is bigger, the error is bigger if the difference between those two images was bigger. So I was trying to make the difference smaller. So that's what we were aiming to do, kind of get to the bottom of this basin. Q. Anyways, so these guys came up with this idea called a perceptron. And a perceptron is a very, very simple version of a neuron, and this is a slightly simplified version of the one that you learn in a machine learning class, because they also include a bias and an activation function, which I'm going to skip over for now. But basically, what you want is you want to kind of use this as a minimizing function. So what you can do is tell it that, okay, this is the value that you're giving me, but that's not the value that I want. What I actually want is 0.4. Now I know that this is the data that you're giving me, so I can't change the data, but I can learn by changing the weights in my data, or in my neuron. So my neuron can look at this data differently by changing to its weights, and learn to give you this output from the data. That actually works relatively simply as well, which I think I may have removed from here. But in essence, what if I wanted to get 0.4 instead? It's giving me 0.2, but I want 0.4. What I could do is look at what's the difference between 0.4 and 0.2, and then propagate this error back to the network and adjust my weights accordingly. So let's look at the worked out example in here. So we may have done this working out a little bit a few times already. So let's just do one step. So let's look at what I want to get. So if I want to get, let's do 0.4, but I'm getting 0.2. So what do these numbers mean? Irrelevant for the moment, but I want to get to 0.4. Wow, this painting here is not working too well with my Wacom. So what's the difference between 0.4 and 0.2? It's 0.2. So what I could do is adjust these weights accordingly. So if instead of getting these values, I want to get maybe some bigger values, well, I could try this. I could simply move my weights in a particular direction. In the same way that I moved my X and Y values in a particular direction, I just made them bigger. What if I made my weights a little bit bigger as well? So the difference between 0.2 and 0.4 is 0.2. So what if I make this minus 1.2 and this one I made plus 1.2? And we update this calculation accordingly. 1.2, 1.2. So 1.2 times 0.3 is minus 3.6, I think. And 1.2 times 0.5 is, sorry, that's not right, 0.36. And this one is plus 0.6. So if I add these two together, minus 3.6 plus 0.6, I should get to 0.24, I think. Okay. Which is not 0.4, but it's a little bit closer to 0.4. So I could now look at, well, what's my error between 0.24 and 0.4, the target number that I want. And the principle that we're doing here is that we're looking at this error. What's the difference between these two guys, my actual value and my desired value? So my new value is 0.24. And then I take this difference and I back propagate it through this one neuron in here. And that's our back propagation. That's a terrible handwriting there. We'll come back to that. So we're taking our error and moving it back through the network. So this is an example of supervised learning, because I've got data, I've got something that can learn, a perceptron, but it's supervised in the sense that I'm telling it what result I actually want. So I'm telling it, don't give me 0.2, give me 0.4. Just learn to give me 0.4 from that kind of input data. So I adjust my weights and hopefully it will get me that. If you want to learn more about neural networks and how to play with them, here is a good video, not a video, sorry, a resource for you, which is Playground for TensorFlow. I'll drop this into the chat as well. Where my chat is? Where's my chat? Chat. So what this one is doing here is basically it's doing a classification example. So you have some neurons, and if I just get rid of all these hidden neurons in here, and let's get rid of this one as well. So for example, if I have data sets like this, and this is what I believe I can do. If I just draw a line between the two, will I be able to classify it? Let's try this. Yes, pretty good job at classification, okay? Whereas what if I have data set like this, and I try to classify it with just this one neuron? It won't classify it because this data set has some yellow values here, some yellow values here, and blue ones here, blue ones here. I can't use this one neuron to divide these two values because they're all over the place. If I have two neurons, then maybe I can combine. If I have a neuron like this and a neuron like this, one of them classifies things left and right, one of them classifies things up and down. Maybe together they can begin to classify things. And I think it's not doing a good job. But would I be able to take some combination of the result if I add more layers to this? So I take the combinations of these results and keep adding more neurons in this. Eventually, I might be able to begin to kind of add more complexity of this. So here, what I'm doing is I'm taking the input or this output of these neurons, and I'm combining these neurons into a bigger network. So I'm learning each step of this. I'm learning the weight of each of these connections. And this TensorFlow website shows you quite nicely that the thicker weight is a stronger connection, a thinner weight is a weaker connection. And the color in here represents whether it's a negative or positive value. So you can see with these two networks and this one extra layer with extra two networks, extra 2 neurons, it manages to classify things a little bit better. So, but it is doing the same thing. And this here shows you the error. So it's counting like how many blue values have I managed to overlap with blue, how many have I managed to overlap with yellow. And it's found that maybe this kind of combination of this and this, combining those outputs of these together, gives me this kind of output where I can get like a blue stripe going in the middle. Doesn't classify all of them. Hence, I still have some error. There's a loss, there's an error, but it has minimized it. It's managed to get most of these blue ones. I can add more complexity to my network. Let's add one more hidden layer, see if that helps. Maybe, I don't know. A lot of the times it's like we'll find out. Yeah, it's doing something. It's managing to capture these, but it's not doing a good job with those. But if I add more layers and more neurons in each layer, eventually it can begin to combine these weights in a way that hopefully gets most of these classifications for you. So neat. Now, so that's the underlying principle of networks combining together. Sweet. Awesome. So let's go back into Nuke. So what we're doing, we were doing a very simple example of how this error is actually propagated back through the network, simply by kind of, let's just see what the result is, plug that result into here. Let's see what's the result now, put it back here, update our values, see what the new result is, and keep reiterating this. So there is an iteration involved in learning. You have to keep learning, and there might not be any end to the learning. You just keep learning until you're happy that you've learned enough. It's like, this is a good enough result, which is important as well, because not necessarily, a compositor approach as well. We usually like things to be perfect, but at the same time, most compositors as well have to kind of think like, is this good enough? So we are kind of used to that as well. Anyways, so that's how multi-layer neural networks work. So now we know that as well. Happy days. And here's, on the TensorFlow website, you can play with them. Quite fun just to see what they do. So what does any of this have to do with images and pictures? So let's look at that. So first of all, I will show you this node in here. This is a matrix node. Now, I'm not going to go through a very thorough explanation of how the matrix node works, because I will be doing that in the next webinar. So if you go to Escape Studios VFX events, and which comes up with the FX courses website, the next webinar I will be doing 2 weeks from now is about, 1 week from now, next week, is about the matrix node. So please come back then and I will explain exactly how the matrix node works. Anyways, but in simple terms, a matrix node connects a pixel with its neighbors. So here I have connect every pixel with one neighbor from top and above, and one neighbor bottom and below, bottom right. And I'm just taking an average of all of those values. So I'm adding them together and averaging them. But I could also subtract them from each other. So for example, I'm adding together the current value and the one below, but I'm subtracting the value from above. So what will happen in these kind of cases is, if there's a difference between bright and dark edge, like over here, it will do a little bit of an edge enhancement for you. So you see, this is because I'm doing this for every pixel. This happens all throughout my image. So this is a tiny filter, and it just works in this small region around every pixel. So like a 3x3 region around this pixel. So over here, very little happens because there's very little variance or difference between those images. There's another example. If I just subtract a pixel on one side of my middle pixel from a pixel on the other side of my middle pixel. If those values are similar, I will have a very small value. If there is a big difference, then I will get a big difference. I will get a negative difference or a positive difference. But this way you can start to get these kind of edge detect tools, right? Or if I take a different connection in that regard over there, I will get a different edge detection tool. So you can see with this very simple, I'm connecting this pixel with another pixel, and you can think of these things as weights. So this one, it has a weight of -1, this one has a weight of +1. So if I go back to my Perceptron in here, this is one pixel, that's another pixel, and these are the weights between them. What will be the final output weight? So that will be the middle value of this. Now, and you can see I can already do quite a lot of kind of, very strong, very visual differences, right? To this whole image, because I'm doing this for all the pixels in my image. But the problem is that I don't know what would be good numbers to put in here. Also, I don't know whether I want to actually look at the number immediately or the pixel immediately next to it, or maybe I want to look at that pixel over there. Maybe that's a bit much more important difference for me, whatever I'm doing. So I don't know what these are, but we can tell Nuke to learn those types of weights. So what we will end up, and actually what is kind of sort of hidden inside of the copycat node itself, is a whole bunch of these filters similar to these of different sizes, many layers of them. And we don't know how many. They have sort of 3 options. We have a small model, medium model, and a big model. Happy days. I imagine they will be small, small, medium, and big in retrospect. But effectively, what you will have is lots of connections and layers within them. And not every pixel will be connected to every other pixel. So, but the ones that are connected, you can say, how do those pixels affect each other? So if I have a bright pixel on one side and a dark pixel on the other side, maybe I want to find the difference between the two. So you're combining those pixels with each other all over the image. So for example, you could do something like this, which will be one of the kind of tutorials you will find probably on the Foundry's website as well, which I think I can share somewhere here, is not this example, that's a good example too, but copycat roto. So making mats. So one very classic example of what to do with a copycat node is, if I have a black and white image as an example, but I have a colorful image as a starting point, could you, copycat, please learn a set of connections for this network that would result in those pixels there outputting that value there. So let's say if these are the green pixels over there, then that should end up as black. If it's some other pixels, then this should end up as white. That's my foreground. So what we are going to tell the copycat is like, this is your output. Find this, and it will try to minimize some kind of an error in the background. So let's set up a copycat ourselves. And we'll start with this slightly different toy example. Let's teach Nuke to read, kind of like in that South Park episode. So what do we want to do? So let's just take a couple of letters. I'm just going to do a really small one. I'm going to start with a small, example here as well. And let's go, just move you guys again somewhere here. And just go to the first frame. And let's do, let's just pick a few of these letters from here. So whatever would spell out constant, C-O-N-S-T-A. So C O N S T A. Okay, and I already have the N and T in there. So 6 letters like that. Const and then N and T, I already have them. So I have this, this will be my input data set. And what I would like to do is, because I have bad handwriting, maybe we would like Nuke to give me better handwriting. So let's do text. And my outputs, what I want to have is C. And I'm just going to make this one show me what it is doing. So value message. So now we can see it in here. And I just want it to be center, and this will be 0, 0, 256, 256. So it's right in the center there. And I'm just going to make it bigger as well. So this letter could be like 200. Okay, C. Control C, Control V. I think I need 6 letters. So O, N, S, T, A. And I'm just going to connect all of these as well. So let's see if we can teach Nuke to read our handwriting in particular. And we want to concatenate all of these into a image sequence, because the copycat node likes to have things as an image sequence as an input. So if I take all these 1, 2, 3, 4, 5, 6 and append them to a single image sequence, and just to view what we have done, let's do a contact sheet. Contact sheet, which would be nice if it was 256 by 256 times 2, whatever that number is. 1, 2, oops, 512, 256. Okay, so we can kind of see what the 6 letters are, right? So this. So what I want Nuke to learn is, if I give it this kind of input, it would give me this kind of output. Can you just make my handwriting a little bit better, please, Nuke? Right? And let's see if it can learn that. And this will be the good time to kind of understand some of the principles within copycat. So let's do copycat. Copycat is a really nice way of teaching neural networks. Like it's really nice. It's once you've understood, once you know a little bit about neural networks, the interface is perfect. It's like it's kind of just about enough information so that you can use it without having to sort of worry about how it actually works underneath. So first of all, it requires you to kind of cache some data somewhere on the disk. So I'm just going to drop this somewhere in there, and let's put this in here. Just learn to read. Learn to read. And this is the 3rd time I'm doing this. So I'll just drop it into that folder. So, and I'm just going to do one more thing, which is I'll give it a frame range as well. Frame range 1 to 6, because I only have 6 letters. And I don't want any more than that. Just so that it will only learn from those 6 letters. So some of the settings inside of this. So first of all, let's use a medium-sized network. Let's hope it's fine. And the crop size, this is the one thing that you want to look at. So let's change it. I'm going to change it to something small like this, 64, or let's change it to 32, even smaller. So 32 is about that much, I think. No, that's 68. So so about that much is 32. So it will segment your images into sections like this, and it will try to learn, if it sees a letter T like this, to output a letter T like this. Now I can already predict this is going to struggle, because that's a very small crop. It will see like a little line like that. It won't necessarily know just by seeing this little line if this is letter T or not. But let's see what happens. So we start training, and this is the interesting part for us to look at. So this is the input. This is what we're telling it should make, and this is what it's trying to do. And this is, the error that it is having at the moment. It's really struggling. It is not having a good day. It's like it doesn't really understand what is the underlying principle of going from this to this or from this to this. I struggle with this as well. It's like, is this a line? Is this a letter? I don't know. So the size of the crop in here defines the size of the feature that you're actually comparing. So if you're doing some paint work or something like that, or if you're painting out tracking markers, look at, what is the area that you actually need to look at. So if I change my crop size to 256, which just happens to be my image size already, and I try training again. Now, the good thing in Copycat, you can keep training from where you were, because it's nice, because you haven't lost the training that you've done so far. But I'm going to start again just to have a comparison. So I'm going to start training again. And you can see it's already finding it a lot easier. I'm finding it a lot easier. So if this is my input, that's what I want to make. And this is what it is able to make at the moment. Also notice this is a colorful image, which is inefficient for me because I'm using black and white inputs. Really, I should have maybe used the black and white output as well, just use less channels, but hopefully it will get there. So what it is trying to do is similar to those tiny filters I was using earlier, doing a little bit of edge detection, a little bit of moving this pixel 1 pixel to the left, averaging 2 pixels together, doing this over the whole image. It should eventually turn this letter in, into that letter, or this letter into that letter. But I want my crop size to be big enough to cover the whole letter. Also notice by making my crop size bigger, I have increased my learning time a lot. And this default value here, 10,000, which basically says, let's look at every letter up roughly 10,000 times. That's a setting that's, a good guess. There's no real reason why 10,000 would be a good, good stage for us to stop learning, or, maybe we can stop learning before that. So what we're looking at here is, this was our old graph. It was really struggling to learn. It was really struggling to minimize this error. This time we are learning, and this error keeps getting smaller and smaller and smaller. We can see that this is the output. And if this is the input and this is the output, this output that is getting closer and closer to the output that is desired. The middle one is the desired output. That's what it is giving you already. So it is already getting a relatively good job, right? So it is turning this letter by moving pixels around in this image into this one. So simply inputting this one will output that, and inputting this will output that. So that's really cool. So have we just taught Nuke to make ugly letters into pretty letters? Well, kind of, because that's actually what it is doing. Now, let's see whether this will actually work. I can, you can imagine the drum roll. So what I'm going to do is create an inference node. So this was the learning part. So the learning part is the one that you need a good GPU for, and I think the Nuke X license as well. The actually using the trained network part is cheaper, I think, and it doesn't need a expensive license either. Just checking you guys are still all there. Anything new in the chat? This is cool over here. Cool. Okay. So let's look at this. Let's create an inference node, and let's see how it will infer those letters we were giving it. So if I was giving it, and let's make a constant for this as well. So here's that was my input, and this was what the network generates. So we can see it's generating pretty good, outputs, right? It's like, it's turning this letter N into this letter N, and it's turning this letter S into that letter S automatically. Magic, right? So what happens if I try to do one more letter? Let's do this. Just going to paste it here, just because I want the same paint settings. And I'm just going to draw a letter here, and it will be this, from the same set. Let's do another letter S in here. Let's look at that. Wow, looks nothing like it, right? It's because this is called overfitting. We had a very small number of examples, and that's now what it's trying to kind of give you as an output. So if this was the input, that's the output. Not great. Let's try another one. Let's try the letter O. Yeah, you can see I'm kind of painting this live. Yeah, let's try letter T. So what actually happens is that it was looking at both what the letters are, but also where they were. So if it's like in the middle, so this T was quite down there. So if I draw the T further up, or actually I drew a totally different T letter as well, it doesn't understand that this is letter T, but it was trying to push those things around. But it's still kind of cool. So if you want to, so here's some other examples of that. We can learn things, but that's not, you have to understand that it needs good examples too, and it needs variance within your examples. So if you wanted to teach it to read properly, you could give it the MNIST data set of all sorts of different numbers. So this is a classic machine learning test. So all sorts of different variants of letter 2. So I would struggle to recognize if this is a 2 or not. But if you train it with enough examples, it will be pretty robust at learning letters. Why would we need this? Well, not really. But the point is, if we move on to some more practical examples. So for example, if we wanted to remove this guy's bracelet, how could we make our life a little bit easier? So first of all, I want to paint just some frames. Because if I was to paint every frame, well, then I wouldn't need a neural network, right? So I want to paint just a few frames and then see whether it can interpolate or extrapolate between all those frames. Whether it can learn to give me, if I give it an input, here's a picture with a bracelet, whether it can give me a picture without a bracelet. So the first thing that you can do to help your neural network is to stabilize around the area that you actually want to modify. So these are the frames that I've chosen, which I think I've stuck somewhere in here. So just 7 frames, but they're pretty bad paintwork. But what I've done is I've stabilized them. So the network doesn't have to search all over your image. So because that was the kind of issue as well. If I draw this letter A slightly above to where it was, that's already making it a little bit harder. You can do this at the training stage as well. What you can actually do is, if you painted these frames and you wanted this to be a little bit more robust, you could make other copies of these frames by transforming this a little bit and making sure that you do, let's say, we move it 5 pixels that way and make another copy, and we rotate it, a few degrees that way. So just to have a few different, whoa, too much. Few degrees that way. So just to kind of have a little bit more variance in your positions and rotations and things like that. And then you do the same for the outputs as well. So inputs and outputs. That's a technique called data augmentation. So you have a set number of data, but you might want to make it look like you have more data. You augment it. You add some variance yourself. But the idea is that we want to train this network. Now, I don't want to train it on this whole image because, first of all, I want to stabilize it. I want it to kind of really learn around there. I don't really care if this network learns that if this is my input, this will have to be my output. Because at that moment, it's actually learning something that's not necessarily useful for me. It will learn that the best way of giving me results most of the times is to just give it the original footage. So if this is my input and this is my output, it won't actually learn anything useful. So what you want to do is you want to kind of crop into the area where you're actually doing a paintwork. Now you may need to think what's the kind of good size of this. I might actually, might be better with a slightly bigger crop because maybe some of this lighting information in the arm is relevant to this area as well. But I don't need the network to learn that if I get a green screen background, let's output more green screen, because then it won't necessarily learn as much what I needed to learn, which is that if I'm giving you a picture with a bracelet, give me one without a bracelet. So you want to crop to that area where the learning is relevant. Then you train it, and hopefully we'll be able to infer it as well. So let's look at that. Some inference. So we have a few examples. Just look at this side by side as well. 1, 2, still wipey. So some examples. So just did 7 images of with and without the bracelet. So from those 7 images, let's see what the network has learned. So the network has learned that if I have, and the cool thing is, even though you're teaching it in a small area, you can apply it to the whole image. That's really, 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 really nice. So even though the input, you have to match the resolution of the input data to the output data, but in the training set, you don't have to match the resolution with your actual test set or what you actually be using it for. So I can still use it on a full HD image. And it's not doing a perfect job, but at the same time, it's not totally terrible either. It's actually kind of impressive what it has done. So, and this, I think, in my computer, which admittedly is a good computer, this took half an hour. If you do it on a computer without a GPU, it will take at least 300 hours. So machine learning is heavy. You need good computers for this. But what it has at least done, you can still see the ghost of this bracelet there. But at the same time, it has actually managed to estimate lighting information as well. It is making this area here more green and this area here more skin tone. And without me, necessarily telling it to do that area more green and that area more yellow, I just showed it examples. It's like, that's what I would do if I was to paint this out. And just from 7 images, it has learned to do that. Now, if you want to learn how to do paintwork with Copycat better, then again, like I said, I will point you towards some of these tutorials. Here's a good tutorial from the Foundry themselves. I will drop this into the chat too. There it is. Look at this video, really, really good. They also do a little bit of data augmentation because I think there's a shadow issue in this video where they paint out on a frame without the shadow, but then they grade their footage a little bit so that the network could learn what happens if the footage is darker, and they should still get these outputs. Quite clever. So, but the principle is still the same. So what you need to do is you need to give your network inputs. This is what I will give you, and you give it the desired outputs, which they call the ground truth, which is a machine learning word that says this is what you want to get. And what the Copycat node will do is it will go through the network. It will try to learn these differences between the differences between, like, this letter and this letter, and how to get from one to another. So it will try to turn these pixels into these pixels. So you have to give it these paired examples, and this is why this is called the supervised learning. Sweet. Now, and the practical examples of this is you can do things like turn a image which is colorful into an image that is a matte. That's a classic example by giving it a few images that is a alpha channel, or giving it with something that has been painted out, or you've done some beauty work. Classic examples like that. Other examples of how to get paired data. For example, if you wanted to make your upscale node, which already exists inside of Nuke, you just have to think of like, well, what is the opposite of upscaling? Downscaling. So can I do that myself and teach that to the copycat and then tell the copycat to do the opposite. So for example, if this is one of my images and I had another image, let's do a reformat here, and I'll go to scale and I want it to go 1/4. Let's say 1/4 the size. So here's the image 4 times smaller. And just to make them the same format, I will quickly reformat it to be 4 times bigger again, not smaller. But I will break the concatenation with this grade node. So if this is my input, which is this low res image, can you give me this high quality output? So you can make your own data sets. If you can think of what is the opposite direction of what you want it to do. So for example, they have the blur and deblur option. So if I make original images and blur images, maybe copycat can learn to turn blur images into unblurred images. Again, that node already exists. What you could do on your own is, if I have a image and the noisy image, can I make another denoiser? Or if I have a CG render, one frame which is rendered at really, really high quality with full sampling, very little noise, and one with low sampling, can I make an upsampler for my CG renders? So we can make these networks ourselves. Or basically what you need is you need a before and after image that you can compare, and then it will do it for you. And just to close this off, just some examples that I was playing with. So for example, something totally random. Here is Steve Wright's videos from the Steve Wright's book of these karate guys fighting. So I just pulled a key and I just did some eroding and Laplacians and eroding and clamps and stuff to make them look a little bit like lightning. What I then try to tell copycat is, if I have sort of footage of this kind of sticks of lightning, can you output men on green screen? So here's an example. Here is men on green screen. I turn them into lightning. They now look like lightning. And then this is the only input to the inference node, and it's trying to generate men on green screen. So this is the input. This is the output. So you can see it's putting legs and limbs sometimes where they're not needed, but it's just things like if a line is ending, that's probably a limb. If it's not ending, then it's probably the dark shirt or something like that. It's a pretty good output, right? Let's see what happens if you put some actual lightning into this. So a picture of a lightning, and let's make this all nice and dark and stuff, and see whether it can make some green screen men out of that. Somewhere here, I think. So yes, kind of. So just trying to take some actual lightning and turn that into green screen men. So here's the lightning. Let's just get that part out of that. And here is some strange, totally useless, just for fun, really. But can we turn lightning into people? I guess you could do it the other way as well. You could turn people into lightning, which would be much cooler. But I think this is cool too. And likewise, what if we just draw some people? Can I turn them into green screen people? Yeah, kind of. It's just some other examples in here. Again, totally useless, obviously, but just fun. Here's a cat. Just for those of you who were waiting for a picture of a cat. Yes, there it is. And here, copycat. Good. Excellent. Good. And just one other kind of totally random example is so this one is from Henrik Prosa, who was in this Foundries webinar, so about copycat. And what he did is he did this trick, which is you take lots of circles of different sizes, just do 10 circles of different size, and then you do corresponding numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically what you have is, if we again do this with a little contact sheet on the side, contact sheet, And let's do this 512, whoops, 512 by 512 by 256. And let's say 1 and 2. So what he wanted to figure out is like, can you teach Nuke that small circle means number 3 and the bigger circle means number 6, and anything in between is those numbers in between. Now, Nuke won't learn the meaning of size. Nuke will learn to take a circle of that size and push those pixels around until it makes the shape 6. Using those edge detection filters, using those filters that move things by 1 pixel this way, 1 pixel that way, it will, and because we have a lot of them inside of this network, like loads of them, and it's doing the weightings themselves, then maybe it can. No worries, Raf. Thank you very much. There will be a recording for this as well later. So the truth is, yes, it can. So here is an example. So I have some circles coming in, and numbers come out. Okay, and beyond 9, you just get nothing because I only gave it nine numbers. So, for example, if you have some circles that you've done with some particles and stuff of different sizes, just flying around like that, could you use the neural network to turn those into numbers? Yes, you can. And the different size numbers, or the different size circle as a starting point, gives you a different size, like a different number as an out point. And any numbers that were too big, or the circles that were too big, it just doesn't know what to do with that. It will give you some mush like that. Or if you're ever faced with a reason, I don't know why you would need to do this, but if you need to put numbers onto people, then you could try to key these people. Again, just try to erode them and just kind of get some alpha channels out of this, and eroding it and eroding it again. Eventually, you get their maths turned into circles. Can we turn those circles into numbers? Kind of. And then we can put them over this thing in here. And what we should now have is some numbers on top of people. Hopefully kind of tracking as well, relatively well. Totally useless, obviously, but the next Matrix film is coming out soon, so maybe they would need this trick. So, but why I'm showing you these examples is that with neural networks, you have this the basic ideas. Give it inputs, give it outputs. So if I give it noisy image and a not noisy image, I can learn a denoiser, or I can learn a regrainer, which is also a good thing to have. But you can start to think outside of the box. So for example, how could I make a read time node, something that would slow down my footage? Maybe what I could do is take the current frame and just the luminance, put it into the red channel, the next frame, put it into the green channel, and the frame after that, and put it into the blue channel. And maybe I could teach it, if I give it just the red and blue, to give me the green, right? So to give me the value in between. So then if I just need to give it 2 pictures, after that, shuffle together, maybe it can make an in-between value, So, there's engineering involved in a lot of this, but starting to think about a little bit out of the box. And yes, this is basically the introduction to machine learning with a totally abstract concept in the end. But what is happening underneath is that you are giving your network an input and a desired output, and it will propagate these errors through this network, learning along the way how to connect itself to give you the output that you want. And this backpropagation is also part of this idea of minimization. You're minimizing the error between what you want as an output and what is it's giving you as an output for the moment. So you're trying to minimize this error. So we learned this idea of optimization and gradient descent. So we are trying to minimize this error. And the copycat is part of supervised learning, which is that you have to give it an example of this is what we want to get. This is where we're starting from. And that's everything I wanted to say.